No. So there's 6 of you so far. All right. Maybe I should not have bothered with this lecture, huh? Not enough interest.
We hope to learn something.
Since you guys showed up, I'm going to do all the good stuff today. Okay. So, any questions about the SVM lecture from last time? Those of you who were there. Okay. Okay. So today, today's lecture, as I mentioned in my email, I'm just going to give a 1 or 2 page overview of a few different topics. Like they're more advanced material, but it's still something that is not that far off from what you've studied so far in 490. So if you wanted to learn more about this, you can use what we have in today's lecture as a starting point. Okay, that's the idea. Okay, so the first thing we're going to talk about is semi-definite programming. So what's semi-definite programming? Okay, so it's actually a generalization of linear programming, but a special type of convex constraint that actually allows you to solve a bunch of interesting convex optimization problems. Okay, especially convex optimization problems involving norms of matrices, like the spectral norms of matrices, and that's why it's been when it was first introduced, it didn't see too many applications, but more recently in the context of matrix completion and things like that, and other interesting machine learning or signal processing problems where these kinds of convex optimizations problems arise. Okay, so what's the problem? So the problem is you have a linear function, C transpose X, but then your constraint is written in terms of the semi-definiteness of a matrix. Okay, and what's this matrix? F of X. F of X is a matrix that might have a constant component here that's not a function of X. And then the rest of it has each of the, so this is a linear combination of other matrices. And the Xi's, so Fi's are, the G's and the Fi's are M by M matrices. And these Xi's, X sub I is basically the components. These are scalars, right? That's just the components of X. Okay. Right, and this constraint that this matrix F of X is I guess in this case a negative semi-definite, is also known as a linear matrix inequality, because sometimes the same problem is written with a positive semi-definiteness constraint, and you can easily convert that into a negative semi-definite constraint by putting a negative sign in front of the matrix. Okay, so it's the same thing. So this is also known as a linear matrix inequality, or LMI. Okay, so that's another way to describe a semi-definite program. Why is this a convex optimization problem? Of course, it's a linear objective function, which is a special case of convex, and it's over a convex set. So this set where f of x, the set of x's for which f of x is negative semi-definite is a convex set. And why is it a convex set? Well, you can just easily verify the convexity condition. Okay, so if I have two x and a y, for which f of x is negative semi-definite and f of y is also negative semi-definite, then for any alpha between 0 and 1, I need to look at the convex combination and show that that's also negative semi-definite. But that's not that hard to see. You can write this as g plus the summation I equal to 1 to n alpha g, sorry, it's not g, alpha xi. I will get to the alpha g in just a second. And then I can split this into alpha g plus 1 minus alpha g. Okay, then I can easily now see that this is just alpha f of x plus 1 minus alpha f of y. Okay, so which since f of x and f of y are both negative semi-definite, and I'm taking a positive combination of them, these coefficients are non-negative. This whole thing is going to be negative semi-definite. Okay, that clear? All right, so this is a convex optimization problem. And in fact, you can take multiple linear matrix inequality constraints like this and combine them into one. Okay, so I could have replaced this by a bunch of constraints that are of this form, and I can combine them. And that's not that hard to see, because if I have, say, f tilde, which is g tilde plus a linear combination of f tilde i's, and the same thing with the hats, which are both negative semi-definite, then this is equivalent to saying some other matrix f, which can be written as g plus a linear combination of fi is negative semi-definite. If I define the g's, in what manner? How should I define my g in terms of g hat and g tilde? Yeah.
Stack on top of each other.
I couldn't hear that. Let me increase the volume here. Yeah. Say that again. Say that again, Chelsea.
Just put them on top of each other.
Putting on top of each other, that will not necessarily satisfy, but there's something else you can do. It's similar, that you can ensure that the when you put them together in that manner, that you will get a negative definite matrix. Any other ideas?
Oh, the diagonal, maybe?
Diagonal, yes. They can put them on the diagonal. So put g tilde here, g hat here, and 0, 0. And the fi similarly. Fi tilde, 0, 0, fi hat. And so then you can see from the fact that if these guys are, each of these guys, I can write that as a combination of these, and the fact that the g tilde plus the linear combination of the fi tildes is negative definite, and then the g hat and the linear combination of these are negative definite, implies that this matrix will be negative definite. Okay. All right, so that's one way to capture multiple LMIs into one. Okay, but why is STB framework important? Because it actually captures many interesting convex optimization problems. Okay, and there are efficient computational methods to solve STPs. Okay, using interior point methods. Actually, it's basically what I called primal dual interior point methods. Now, if you want to learn more about that, there are some details, more details that I'm going to cover today in the book by Boyd and van der Berge. And there's actually a very nice tutorial article by the same authors, Boyd and van der Berge, on STPs. That's probably around 10 or 15 years old now. And they show, they talk about computational techniques as well in that. And if you use MATLAB, there's a package called CVX, which was again developed by Boyd at Stanford University. And the CVX package actually is largely about solving STPs, because the STP framework generalizes a whole bunch of interesting convex optimization problems. Okay. So what I'm going to illustrate here is a couple of examples, and these are basically textbook type examples to show that STP generalizes some common optimization problems that you've studied in a basic course on optimization, such as linear programming. So if you look at linear programming, so we can always write linear programs in this manner. Okay, either the linear program itself or its dual can always be written in this manner. You're minimizing linear combinations subject to an inequality constraint like this. And this inequality constraint, remember, this is basically saying that if the rows of the A matrix are A1 transpose, A2 transpose, and so on, this is saying that A1 transpose X is less than B1, and so on up to AM transpose X less than BM. So these are all constraints of this form, or I can write this as minus B1 less than 0 and minus BM less than 0. So I can write these constraints trivially by forming a diagonal matrix with these components and making that diagonal matrix negative semi-definite. Because a diagonal matrix, its diagonal elements, its eigenvalues, and if the diagonal matrix is negative semi-definite, that means all of those eigenvalues are going to be negative, right? So this is equal to saying that the diagonal of the matrix, or the diagonal matrix with AX minus B, the vector AX minus B on the diagonal. That means this is basically A1 transpose X minus B1, AM transpose X minus BM. This is negative, semi-definite. So you convert a linear program into an STP that way. Okay. But here's another example that's not so obvious that you can convert into STP. Okay, so here you're trying to minimize a quadratic here. This is a quadratic optimization problem subject to a same linear constraint. And this quadratic is being divided by D transpose X. Actually, this is not a quadratic optimization problem. I'm dividing by D transpose X here. So this is a convex, can be shown to be a convex optimization problem. And we assume that this D transpose X is strictly positive whenever the constraint is satisfied, so that this whole thing is positive or non-negative. Okay, and I'm not dividing by 0 because I'm making this strictly positive. So this is the optimization problem. And again, the trick here is to use an auxiliary variable to convert, to basically upper bound the objective, okay? And we used this kind of trick in the last class, if you were here last time. So if in the SVM problem, if you remember when we wrote this optimization problem, so we had this max-min optimization problem, and we rewrote that as a maximization, we introduced a new variable, psi, okay? And we wrote that as a maximization of psi subject to, we absorb this minimization thing into the constraints. So you want this to be bigger than psi for all I. So we can do something similar here. This is actually a pretty standard trick, that we can write this as minimize t, where t can be thought of as an upper bound on the objective, such that subject to ax is less than b, and then we write this less than t, like that. Okay. Now I've introduced another variable, so I minimize this over x and t actually. Okay. All right. So this actually can be written as minimize. I claim that these constraints together can be written as an STB constraint. So this part is linear in t, and of course x, because it doesn't involve x. Trivially. So we can write this as diagonal. To take care of the first constraint, I can write this as diagonal ax minus b, and then I put zeros here. And then what I do to take care of this constraint can be thought of as C transpose x squared less than t times d transpose x. But I can capture that through a negative semi-definiteness constraint by putting stuff on the diagonal, because this has to be a symmetric matrix. So I'll make that C transpose X here, C transpose X here with a negative sign. Negative sign because that will make sure that this thing, when I convert the negative to positive, I will get something that is, when I take the product, it'll be of the product of this times this minus this time this is positive, and that exactly gives me this constraint. Okay. Okay. There are many more interesting problems that can be written as STPs, especially problems involving the spectral norm of matrices. So if you're interested in reading about more of this stuff, and again, look at the, I don't remember which chapter in Boyd's book. I don't have Boyd's book in front of me right now. But you can search in the at the back for in the index for semi-definite programming, and you'll see more examples in the book. Okay. So any quick questions about this technique? And why again, why is it useful? Useful mainly because there are efficient ways to solve STPs.
Did you mention the motivation behind the form of example 2?
Oh no, it's just it's a textbook example to show that something that doesn't look obviously like an STP can be converted into STP.
Okay.
All right. Let's go to.
So for last example, why do you introduce the auxiliary variable t?
Oh, to be able to write it as an STP. So I can take this thing that is this guy, which is, first of all, it's not in the form of STP because this is not linear, right? So I want something linear up here. So I take this and use an upper bound on this and make that into a constraint. Okay. And this is a standard trick. So basically by minimizing t with this upper bound, you're making sure that this is small, right? You're minimizing this as well. Okay. All right. So now let's, if there are any other questions about this? Okay. Now let's look at another topic, which is related to something we studied in class. And that's the method of multipliers, right? So if you look at the method of multipliers, and I'm going to add this term alternating direction to it. And I'll tell you what that means in just a second. So you want to minimize some function subject to an equality constraint. And typically this equality constraint is a linear constraint, okay? And you did exactly this in computer assignment 3, right? Use the method of multipliers with ax equal to b as the constraint. And you saw, as you saw in your assignment, if you look at the augmented Lagrangian, so here's you have this penalty term added to the Lagrangian for some c, or you can actually make this ck and let ck grow with k, okay? But as long as c is large enough, okay, then this iteration, the method of multipliers iteration, where you minimize this augmented Lagrangian to find your x for iteration k, and then you update your Lagrange multiplier using the dual, right? So in fact, we showed that this h of x really corresponded to the gradient or subgradient of the dual, right? So we have this iteration, which I didn't prove this in class, but you can show. You kind of showed this, at least you in your computer assignment, that if this function is convex and h of x is of the form ax minus b, it doesn't have to be of this form. It can be generalized a little bit, but certainly if h of x is of the form ax minus b and f is convex, you can show convergence to the optimum for c large enough, right? Okay. Now there are interesting examples that arise in practice where the function being optimized and the linear constraint are decomposable, okay? And this specifically, these kinds of problems might arise in distributed, when you're looking at distributed settings, where you're minimizing a combination or a linear combination of functions where each function is controlled by a different variable. And maybe think of observations being taken by sensors in a distributed sensor network, and there's a local objective at each corresponding to each sensor's observation, and what you're trying to minimize, say something like a mean squared error in an estimation problem that you're trying to do. That mean squared error can be written as a linear combination of convex functions. So it could be some fx, f that's controlled by a variable x, and g that's a function of some other variable z. Okay, and subject to again a linear constraint, but that's also can be written in this form. Okay, and I just showed it to you for two functions, but think of it more generally, that you could have, m different functions, each one controlled by a different variable. Okay, different x's. Okay, here we have x and z. Okay, so now you can construct an augmented Lagrangian for this, just like we did here for the method of multipliers, right? So, okay, so I can do that, but now instead of just having f of x, I have f of x plus g of z. So the function is a function of two variables, x and z, right? X and z. And the augmented Lagrangian has some lambda here, and then fx plus gz plus lambda transpose times the constraint function. And then you have the penalty, which is the constraint function norm squared. And I multiply that by c. I purposely put a 2 here just to compensate for this 2 and when you write down the iterations. Okay, so so that's just for convenience. Otherwise, you'd get a 2 times c here, right, from the h of x squared. So this is typical to put to a c over 2. I think we did this in class 2. Maybe an example. Okay, so what's the difference? So I could have actually done this kind of iteration, minimization of a joint minimization of x and z with this. So maybe I'll just write that down here. So I could have done a joint minimization over x and z like that, and then continued this way. So this h of x would be basically, in that case, ax k plus b zk minus b. Okay, and doing it this way is just applying the standard method of multipliers to this optimization problem. But if I did this, I didn't really exploit the fact that the function was decomposable into the sum. Okay, so it turns out that you don't have to do this joint minimization. Okay, especially if we're looking at high dimensional problems where the x's and the z's are high dimensional, and now or I could start with a vector x that's very high dimensional, but if I could break it up into little pieces and write the function as a function that's only controlled by these little pieces of x, then doing this joint optimization might be hard, but maybe I can optimize over the x and the z separately. Okay, so that's the idea behind ADMM. Okay, the idea is that you can do a separate minimization over the x variable. By looking at the previous, plugging in the previous iterative z, and the minimization is only over x when you produce the next iterative x, the x variable. And similarly for z, you do a minimization only over z to find zk. So in this case, you put xk here, z lambda k. And then the lambda k iteration is as before.
Sorry, shouldn't it be xk plus 1 in the zk plus 1?
Yeah. This is how it doesn't really matter. This is how it's written. You can this is how the ADMM iteration is written.
Okay.
You can still show convergence. Okay, so what you can show is that this thing actually does converge for this iteration converges again if C is large enough and your the functions of course f and g have to be convex. Okay, so that's this is ADMM, and ADMM has actually found a lot of applications recently, and especially in the context of distributed optimization. Okay. Yeah, if you do a Google Scholar search on ADMM, and you'll find hundreds of recent papers on this topic. And so maybe some of you are using it in your projects. Okay. So that's the idea. Any questions? There is a discussion about ADMM in your textbook, by the way. Don't remember which chapter it is, but yeah. So and actually a proof of convergence and so on. Next topic. This is actually a very interesting topic. Accelerated gradient descent. Very unusual idea. Okay, very creative idea. All right, so we saw gradient descent, right? Xk minus alpha k times the gradient. And if f is convex and has Lipschitz gradients, or if it's called L smooth, it's another way of saying it has L Lipschitz gradients, then we know that we have 1 over n type convergence, right? So fxn minus the optimum value goes to 0 as 1 over n. Okay, as long as this alpha k, you don't have to make alpha k go to 0. You just have to you don't have to choose a varying step size. I mean, as long as you can just choose a fixed step size, as long as it's between 0 and 2 over L, you guarantee this. And if you didn't know L, then you would just use something like backtracking, Armijo's rule, and you'll still be able to show this kind of convergence. Okay. All right. But is this the best rate of convergence you can get under these assumptions on the function being convex and having being L smooth? Okay, turns out that you can do better. Okay, and a first idea along these lines was given by someone called Polyak in the 1960s. Again, a lot of this work was done by Russian mathematicians. And so there's Polyak and then more recently Nesterov, who really came up with the theory for this. So Polyak's idea was to add something, and he called this term, so adding some memory into the gradient descent. Okay, so make xk plus 1 not just dependent on xk, but also depend on xk minus 1 in this manner. And this is called a momentum term. And the rough idea is as follows. Maybe I should use a different page to illustrate this. Well, let's see if I can draw this right on this page itself. Okay, so you have, say, let's take a 1D example. So I have a function that looks like this, convex function. Okay, and if I if I start somewhere out here with a certain step size, and we saw this for a quadratic example in class. Okay, so if I just did gradient descent, basically what would happen is that maybe I bounce around a little bit initially, and then I might start, eventually just head towards the minimum. But as I make these steps, right, close to the minimum, the gradient is becoming close to 0, close to the minimum. And so I'm not going to actually make much progress. So the progress is going to be really slow as I get close to the minimum, right? With any gradient descent procedure. All right, but you need that to happen in order to be able to converge, right? Otherwise, you keep bouncing around. Okay, so the idea behind the momentum method is that when this gradient is close to 0, okay, having this additional term here, this term basically pushes the xk plus 1 further down, makes it go further down. Okay, so and you can see this here. So let's say, maybe I'll erase this. So suppose I'm this is just a rough idea behind the momentum method. Okay, so suppose I'm here, okay, and my gradient is positive, right, at this point. So when I go in the direction of negative gradient, I'm going to go head in this direction towards the minimum. Okay, but again, since the slope is getting kind of flat here, this the amount by which I progress is going to be small. But if I look at xk minus xk minus 1, the current so xk and the xk minus 1 might have been somewhere here. Xk minus 1, what sign does that have? That's negative as well, right? So basically what happens is that I'm adding a little more to this, I'm giving it a little more momentum in this direction. Okay, and this is sometimes called a heavy ball method, where if you take, if you roll a heavy ball down a slope, it's coming to a flat portion at the bottom of the slope. Okay, versus a light ball. A heavy ball has momentum, so it'll actually, as the surface gets flatter, the momentum keeps it going more than a light ball. Okay, so that's why this is sometimes called a heavy ball method. Okay, so this momentum term allows you to converge a little faster, and this was observed empirically by Polyak, and there was some proof that it actually works for quadratic functions, that it improves the convergence rate. Okay, so basically by accelerating the gradient descent near the minimum. But it was basically Nesterov, who came about 20 years later, who formalized this idea of adding memory to the gradient descent problem to improve its convergence rate. And Nesterov's method is interesting. So if you notice that in Polyak's method, you take the gradient first and then you add the momentum term. And Nesterov's method, you actually add the momentum term first and then take the gradient. Okay, so that's the idea here. So to form the next iterate, xk plus 1, you write it in terms of some new variable yk and the gradient of yk. And here Nesterov just, and this is one of the methods, because there are many variants, by the way. I'm just giving you one of the basic methods that Nesterov suggested to use for accelerating gradient descent. Here, so basically it's like alpha being 1 over L in this case. And then there's this coefficient, let's call this coefficient lambda k minus 1. What is it? Looks bizarre here, but really you need this form to be able to prove convergence and convergence at a faster rate than 1 over n. So this term, let's just call this, say, mu k plus 1. Okay. So this lambda k is a coefficient that has a recursion of this form. Okay, you plug that in here and you get this yk plus 1, which is kind of uses both xk plus 1 and xk. So there's some memory in my yk process. Okay, and so if you look at, if you just call this coefficient here, this lambda k minus 1 divided by lambda k plus 1, and just call that mu k plus 1, then I can write xk plus 1 as xk, yk is the same as xk plus mu k times xk minus 1 minus 1 over L, the gradient of f at xk plus mu k times xk minus 1. So this momentum term, if you want to think of this that way, okay, so the momentum term is sitting inside the gradient. Actually, it's actually also sitting outside the gradient, like in Polyak. Okay, so you're modifying the gradient descent in two ways. But more important, the big difference between Polyak's momentum and Nesterov's momentum is that in Nesterov's case, it actually goes inside the gradient as well. Okay, And what Nesterov was able to show, and this is the beautiful result, and you can, again, there are lots of papers that talk about this result and try to understand why it works and so on. So you could do Google Scholar search and find a bunch of papers on this topic. But basically, he was able to show that you can improve the gradient descent convergence from 1 over n to 1 over n squared. And he also showed that this is the best rate you can get. Okay. So you can't improve it any further under convexity and smoothness conditions. And another interesting thing is that this kind of acceleration, these are called momentum methods, they also can improve convergence when you have strong convexity. Okay, you get a better coefficient for the linear convergence rate. Okay. All right. So kind of understand a little bit about what's going on here. I mean, there's a whole bunch of literature on this topic. So I could probably have used maybe a third of the course to talk about this if I wanted to. But so it's a rich topic. But if you want to read more, this should provide you with some basic starting point. Okay. Any questions?
Does conjugate gradient method use this idea, or is it different?
Which quantity?
Conjugate. What was it?
No, conjugate is slightly different, and was mainly used. It's for quadratic problems where you can get fast convergence similar to what you get with Newton's method without having to do an inverse of a Hessian. Okay, so that's actually, I'm not going to talk about conjugate methods, but conjugate gradient methods. But I believe the textbook has a discussion about conjugate gradient.
Okay, thank you.
It's different, yeah. Okay. Any other questions?
Yeah, I have a question, Professor. I guess the intuition here, I guess the methods take inspiration from a dynamical systems approach, where
Exactly.
like
Yeah.
a ball running down the hill kind of thing, right?
Yeah.
So lately I've been wondering around these ideas because I'm a controls person. I'm working on the optimum control and trajectory optimization, and thinking about this problem lately, and thought maybe I could use some of the ideas from dynamical system theory to apply this, optimization over finite spaces. And I'd like to ask, now seeing this, I'd like to ask that where exactly should I look for in order to,
there are a bunch of papers that do exactly what you're saying, which is to understand why these momentum methods work, and based on actually converting this into a continuous, actually looking at it in continuous time rather than discrete time. I think one of the initial papers was by Boyd, so you can do a search on this, but just search for maybe it's a combination of dynamical systems and momentum methods and gradient descent.
Yeah, I actually found a couple of papers, but seems like the research on this seems to have ceased around 90s or at the beginning of 2000 or so. So is there any specific reason for that? I guess that the
reason I think, and this time again a guess, is that I think that people didn't believe Nesterov's methods, that believe that they actually work, that and I think so they were trying to find some explanation because it seemed to be like magic initially, why it works so well, and so I think there was a rush at one point to try and figure out, maybe some other the way to look at this to understand why it works so well. And so, but one thing is, when you apply these accelerated methods in the context of stochastic gradient descent, which is again, which is the next topic I'm going to talk about, then there are issues to consider, and maybe your dynamical systems approach can help there. I don't know how much of that has been studied in the context of stochastic gradient descent, and also in distributed settings as well.
Yeah,
There is some, maybe there are some open issues in those settings to understanding, how to make these accelerated methods work in the best possible way in those settings.
What I like to add is I kind of feel, have the intuition that maybe treating this whole optimization thing as like intelligent agents seeking for the smallest or the lowest point of some valley, and maybe we can use some there are some meta heuristics method that try to look for global optima of some function, and they treat the problem as like multi-agent systems trying to search over the entire state space, each one of them communicating with each other and saying what they found, kind of like that. I guess this kind of looking this kind of perspective, I guess, has the potential to excel at global optimization methods.
Right. I think that's the key. I think when you apply things like stochastic gradient descent in the context of for non-convex optimization problems, which I'll talk about in just a second, then it turns out that it's been observed empirically that these methods can escape local minima or bad local minima or saddle points very effectively. And so maybe some kind of dynamical systems perspective would shed light on that. So I think that people are looking at those kinds of problems right now. So
thanks a lot. Definitely a cool way.
It's definitely worth exploring. Yeah. So actually, speaking of which, let's talk about stochastic gradient descent, at least in a form that arises in the context of machine learning problems. So maybe to see that, we briefly mentioned this in lecture 9 when we talked about backpropagation in neural networks. Okay, and I said that, let's see, right, there's the function here. Yeah, this is the function. Right. So this, if you remember, this, we had a loss function. An example of that is the squared loss, and this loss function can be written as a sum. The overall loss function is a sum of capital N pieces, one piece corresponding to each training data point. Okay, so you have the sum of these guys that defines the objective, and I want to minimize this objective over the functions over the parameters of my neural network. So W's the weights and the bias terms B. Okay, and we said we could use a gradient descent procedure to do this. Okay, so what is stochastic gradient descent in this context? Okay, so you have this form, the form similar to what we had for the neural network optimization problem, right? So you want to, I publicly wrote it as an average. You typically see this as a sum, but there's no, it's a finite sum of a finite number of things. It's minimizing the sum is the same as minimizing the average. Okay, and I purposely wrote it as an average so that we can introduce a stochastic notion in this optimization. Okay, so this function f, which is written as the sum of these m, or the average of these m functions, fi. And the gradient is a linear operation, so the gradient of this average is the average of the gradients. Okay, which is the gradient of f. Right. Well, I should have put it on the left-hand side, but this is f. Okay, so the gradient of f is the average of the gradients of the fi's. And so if I do gradient descent, I can think of the gradient descent with, say, alpha k as my step size at time k. I can write this as alpha k times 1 over m times, so the gradient of f is replaced by the average of the gradients of fi's. Okay, so that would be the gradient descent, and this is exactly what we tried to do. We tried to compute this this gradient term in using backpropagation, right? So, okay. So in stochastic gradient descent, what you do is rather than using all these terms, all these gradient terms to do the gradient descent, at time k, I'll choose one of these terms in the summation at random, okay, and use only that to compute the gradient step. Okay, so stochastic gradient, I go this way. Instead of summing over I, or taking the average over I'll just look at one of the components in that average. Okay, let's call that ik. So ik is some index in the set 1 through m. Okay. So this is the chosen index at time k. And there are, of course, a couple of interesting ways to choose the index. One is to just choose it in a cyclic manner, right? So just start with 1, 2, go up to m, and then when you exhaust it with m, go back to 1, and so on. Or round robin. The other more interesting way is to choose this ik at random. Chosen uniformly at random and independently in each time step. Okay. Now, if you choose it uniformly at random, then I'm choosing a particular index with probability 1 over m. Okay, so does everyone here have some familiarity with expected values and probability and so on? You've taken something, right? Like 313 and ACE. Okay. So basically, the expected value of the gradient I should not write it as fk, but it should be fik, I guess. It should be fik. Okay, because ik is chosen uniformly at random. It's 1 over m times I equal to 1 to m. Right? Each one of those indices is chosen with probability 1 over m, which is basically the gradient of f. So what the SGD is doing is that it's when ik is chosen at random, it basically uses an unbiased estimate of the gradient in place of the true gradient, and that's why it's called stochastic gradient descent. Now, this is only one way in which I could convert a gradient descent problem into a stochastic gradient descent problem. More generally, I can think that I'm doing gradient descent. I didn't have to actually think of f of x as being composed as this average, but what I could instead have is just start with gradient descent, which would have been xk plus 1 equals xk minus alpha k times the gradient of f. But rather than having gradient of f, okay, I have some noisy version of gradient of f. So this gets replaced by gradient of f plus some noise at each time step. Okay, that should be k here. Right? Then you can call that noise term some psi k or something. So that's another way of thinking about stochastic about this gradient descent when you have when you're trying to minimize an average, because this can be f of ik can be thought of as a noisy version of the true gradient. Okay, in the sense that it's like I'm adding zero mean noise in some sense to the true gradient to get my f of ik, because the expected value of f of ik is equal to that. Okay. Okay. So that's the idea. So that's why. So the trying to minimize an average of functions like this, where I just use one of the functions in each gradient step, can be thought of as a special case where I'm doing gradient descent, where at each time step, I'm using not the true gradient, but a noisy version of the gradient. That's why this is called stochastic gradient descent. Okay. So any questions about this setup? Okay, but I purposely use this form to introduce stochastic gradient descent because this is the form for my function that is most commonly used in machine learning, and it's in that context that stochastic gradients has gained a lot of popularity in recent years. Okay, but if you really want to think about the most general form of stochastic gradient descent, it really corresponds to replacing the true gradient in gradient descent by some noisy version of it. Okay, so what's the advantage of stochastic gradient descent over the full gradient? And the big advantage is that computation, right? So computation per iteration is independent of m. So m is very large, as you would have in the context of machine learning with lots of training data. So the computation per iteration is not going to be a function of the number of training samples that you have. Okay, and correspondingly, of course, there's also going to be a lot less memory usage for that same reason. Okay, so yeah, so that's great. But what are some of the drawbacks? Of course, I mean, first of all, is this okay to do? What does it do to the gradient descent? Will it still go to the minimum, and in what manner will it go to the minimum? Right? At what rate, and so on. So the big disadvantage is that you have slow convergence rate, especially near the minimum, which is why I was saying that you might want to look at accelerated methods in the context of SGD. So if you look at SGD, for example, after m updates, the constant step size, say, then SGD after m updates, because in each update you're going to use a different different, you got to use a different iterate, right? So you'll go through, actually this with the random index, but I'm assuming that I've re-indexed things so that I go from 1 through m. Okay, so this is what SGD would do. In each step, so I start with xk, and then I use the gradient of the first function at xk, and then the next, to produce xk plus 2, I'll use the gradient at f of xk plus 1, and so on. So this for the second function. And so after m steps, xk plus 1 will look like this. Or you can view this as what would happen if I did HGD with a cyclic choice of the indices. Otherwise, there's some random combination of so there's some ik, it's just harder to write. So it's ik belonging to 1 through m, and then the f of ik and xk plus I minus 1, and so on. So it'll be a little harder to write, which is why I didn't bother to do it that way. Okay, but what happens with the full gradient? That's what I wanted to compare with. If I did a full gradient, then in one time step, and suppose I use a step size of alpha times m, then I'll get, with a full gradient, I get this. Okay, so basically, what my SGD is doing is adding a term that's very different from what you'd get as the next iterate, and with the full gradient. Okay, and it turns out that this may not even be a descent direction. This, when I take the sum of these guys, it may not be, it doesn't necessarily mean xk plus 1, it will be, it's such that my function at f of xk plus m is less than my function at time k. Even though we are unsure of that, with gradient descent, we are unsure of that, as long as the step size is chosen carefully, right? Below a certain amount. So assuming Lipschitz and so on, and alpha being less than 2 over L, you could guarantee to go down, but with SGD, you're not guaranteed to keep going, keep descending. So it turns out that just like this also happened in another context. What was it? We saw when we had something like gradient descent, but we are not guaranteed to be going down. What was that? Remember what context we saw that? Anyone?
Newton's method?
Repeat.
Newton's method.
Well, yeah, we did that, but more recently.
Subgrading
Methods, right? So what do we have to do in order to guarantee convergence with subgradient methods?
Didn't 0 need to be?
Yeah, so you have to take alpha k to 0. So you have to use diminishing step size. So you really need diminishing step size to converge, and it turns out that you need to do that in order to prove convergence. Okay, but even if you chose diminishing, but the problem with diminishing step size is that you're not going to be able to get the same kind of convergence rate that you would get with chosen beforehand, and that's what happened with subgradient methods, right? So we went from 1 over n to 1 over square root of n type convergence, and the same thing happens with SGD. So and you have to be careful about how you even define convergence. So because there is this stochasticity, right? So it's not f of xn, but the expected value of f of xn minus the minimum, you can show that this difference converges. Actually, there are stronger versions of convergence, which I'm not going to get into. But basically, it's some stochastic version of the convergence result we had before, and you go from 1 over n to 1 over square root of n. Okay. The interesting thing is that even if you have strong convexity, you don't improve the 1 over n type of convergence. Basically, you don't get the what's called linear convergence, or and some alpha to the n where alpha is less than 1 type of convergence anymore. Okay, whereas with regular gradient descent, this would become like some coefficient times to the power n when you had strong convexity, and you don't get that with stochastic gradient descent. You still remain at order 1 over n. You improve a little bit. You can go from square root of n to n, but that's all you can get. So people say, well, how can we improve the rate of convergence? Well, one simple trick, and there are other ways to do this, and there's a whole bunch of literature on what's called variance reduction techniques for stochastic gradient descent. But one simple trick that one can use is to not, well, this is pretty obvious. You don't just use one of the gradients at each time step, but use a batch of them. And these are called mini batches. Actually, using all of the gradients together is called the batch gradient, which is the full gradient. And mini batch is that you take a subset. So rather than evaluating only one gradient, just look at summing over some set, capital Ik, where this capital Ik might be chosen at random from the set 1 through m. And the size of this Ik set is some batch size B, which is typically much smaller than m. Okay, this is called mini batch SGD. Okay, and with this mini batch assumption, you can improve the convergence rate a little bit. Okay, so Lipschitz gradients, you go from 1 over square root of bk plus 1 over k type behavior. So again, as you make the batch size large, closer to the full batch, you're going to get back 1 over k type. So this should be an n, not k. Sorry, I need to fix this. The n. So it's so you get approach 1 over. In fact, here's a picture of something that happens as you increase the batch size. Okay, so this is SGD with batch size, mini batch size of 1. So it's kind of wandering all over the place, right? And that's what happens with the stochasticity. So especially when you're getting close to the minimum, you're still kind of hovering around. Whereas if you use the full batch, okay, then you would do that. This is a quadratic function, so you go nicely to the minimum there. Whereas the mini batch does a lot better than just SGD. Okay, a lot less noisy. So you can think of this mini batching as a way to reduce the variance. So even though the mean is correct, right? The mean of the gradient corresponding to each component is the same as the randomly chosen component, is the same as the original full batch gradient. There could be, if m is large, this quantity, this random quantity, could have a very large variance. So that's why you're hopping around all over the place. And so any method to reduce that variance, and one of the simplest way to do it is to use this mini batch approach, which can improve your convergence rate. Okay, but okay, so why is SGD popular? The main reason why SGD is popular, more than even the computational reduction in computation each time step, is that empirically it's been shown to be able to escape bad local minima or even saddle points. Again, all this randomness, uh, this randomness helps with that, I think, but people don't exactly know why yet it works. So this is an interesting research question. So basically, the idea is that if you did gradient descent, regular gradient descent, you go here, and then you would end up in this local minimum and get stuck there, possibly. But the SGD has been shown to avoid these kinds of bad local minima and then end up here at the global minimum. Or if there are multiple global minima, it actually converges to one of the global minima effectively. And you can avoid things like these saddle points as well. Okay. Intuitively, it seems to be because of the randomness, but exactly why that randomness works to help you, especially in the context of machine learning problems, these high-dimensional problems. Why it works is still an open question, still a mystery. Okay, but that's what that's what people are trying to understand now.
I have a question about the, I guess, notation of the mini batch. Could you go to the previous slide? So
Okay.
yeah, down below, it seems like, so is that like the mini batch currently is on the function instead of on the data? So basically here, the mini batch is basically used like a subset of the
Indices, yeah. Some
FI.
random subset which has size B.
I see. So this is not the exact, so because usually when I read mini batch, this concept is more on the data. So basically we see like a subset of, maybe it's on the, so
yeah, because you can think of each of the components of FI as coming from one of the training data points, and you're taking a mini batch of those training data points to form this sum.
Okay, so basically the key idea is just like if the stochasticity make that to be like an unbiased estimate, then it doesn't depend on the FI or the XI.
It's just that having this B it reduces the variance in the estimator.
I see.
So rather than just, the mean being the mean will still be the same whether you use a batch size of 1 or B, but the variance could be a lot better with the batch size of B versus 1. Okay, that's easy to understand, right?
I see. Yeah, thanks.
And that's why, I mean, if you can empirically you can see that exactly. I mean, it looks a lot less noisy. Right? This is gradient descent, stochastic gradient descent, and this is the batch with some batch. I don't know what the batch size here is. I just picked up a picture from the web. Okay. Almost out of time. So that's all I have to say. And I guess you guys are done except for your projects, right? Which are due next Monday. And otherwise, have a nice, relaxing break, so that come back and hopefully the spring will be a lot better than what the fall has been, especially with this pandemic. I don't know whether we'll have we'll all get our vaccinations by the end of the spring semester, but maybe a lot of us will, and things will start to get back to normal by next fall. All right. Any other I was also supposed to announce that the course evaluations are going to be done online. I guess they were done online last semester too. And so, you probably received email notifications about that. So make sure you take some time to fill them out and give me any feedback. Okay.
Thank you. Have a great break.
All right. Thanks.
Thank you.
Thank you.
Professor, is there any possibility on extending the due date of the project, the deadline, a couple of days maybe, 1 or 2 days?
Okay. Do you have a reason?
Yeah, it's pretty much you know.
Other exams or something?
Yeah, I have a final on Friday, and I also have a couple of similar projects to that I have to write down for other courses, kind of like this one. But other than that, no other excuses. Just asking.
Yeah, I think that should be possible. I mean, I'll just extend it for everybody then to maybe Wednesday instead of Monday. Is that all right?
When was the current deadline? The
coming Monday. So.
Yeah. So 2 days would be great, I guess, if it is possible at all. I mean.
Yeah, that should be fine. Yeah.
All right. Thanks a lot.
Professor, do you have office hour tomorrow?
I can if you have questions.
Yeah, we want to ask about the project thing.
Oh, okay, sure.
Right. Thank you.